EMD electrical machine design transformer output equation page number 445 to 457. Output transformer output equation for single phase transformer, that is expected for 7 marks and 10 marks. Answer questions answer. Output equation for single phase transformer, Q is equal to V2 I2 V1 I1. Q is equal to 4.44 FBM AIT1 into I1. The window and single phase transformer contacts one primary and one secondary winding. Therefore, total copper area in a window is equal to A1 T1 plus A2 T2. That is copper area of primary winding plus copper area of secondary winding is equal to K W A W. W is in suffix. KWAW is equal to A1 T1 plus A2 T2. KW is Windows factor. KW is equal to I1 divided by del 1 into T1 plus I2 divided by del 2 T2. That is equal to 2 I1 divided by del. I1 T1 is equal to I2 T2 del 1 approximately is equal to del 2. So I1 T1 is KWAW divided by 2 into del. That is equal to KWAW2 into del. Q is equal to 4.44 FBM AI KWAW divided by 2 into del. Finally, we find out Q output equation is equal to 2.22 FBM AI AW KW del into 10 power minus 3 in kVA. This is the output equation of the single phase transformer in kVA, where I1 and I2 are the currents in primary and secondary winding respectively. A1 and A2 are cross-sectional areas of conduction primary and secondary windings. Del 1 and del 2 are current density primary and secondary windings. Del is average current value of density. AW is equal to window area in meters square. KW windows phase factor. KW is equal to total conductor area in the window divided by total area of windings. That is equal to total conductor area in the window divided by total area of window. Topic: output equation for three-phase transformer. That is expected for 10 marks questions. Output is equal to 3 V1 I1 in three-phase transformer. Output is 3 into 4.44 FBM AIT1 into I1. AWKW is equal to 2 into A1 T1 plus A2 T2. That is AWKW is equal to 4 I1 T1 divided by del. Q is equal to 3 into 4.44 FBM AWKW del divided by 4. Hint: each window two phases, each limb single phase, two windings in each space. Q is equal to 3.33 F BM AI AWKW del into 10 power minus 3 in kVA, where BM, gel and KW have to be chosen properly for determining the main dimensions. Q equations we obtain three-phase transformer as 3.33 F BM AI AWKW del into 10 power minus 3 in kVA. Choice of design parameters of transformer. First point, windows phase factor. First point, windows phase occupied by conductor material of windings. Second, insulating material over conductors. Third, insulating material between core and limb winding. Second, between LV and HV windings. And third, between HV and two limbs. Fourth point, insulating material and cooling ducts provided between any two parts. Definition: Windows phase factor is defined as the ratio of total area occupied by the copper material of the windings in the window to the window area. That is, KW is equal to total copper area in window divided by window area. Windows phase factor depends upon the voltage. Windows phase factor depends on the voltage ratings of the winding and kVA rating of the transformer. As kVA increases, kilowatts increases, and kVA rating of the transformer on voltage of HV winding increases, K suffix W decreases. As kVA increases, kW increases. kW is equal to 10 divided by 30 plus kVA of HV windings. Note, the above formula is satisfactory for transformer between 15 and 250 kVA. Second point, the above value is decreased by 5 to 20% of transformer rated between 5 to 50 kVA and increased by 5 to 20% for transformers greater than 250 kVA. Transformers design. Choice of design parameters. Second para, specific magnetic loading. Factors affecting the choice of magnetic maximum flux density. That is no load current drawn, saturation limit of magnetic material, iron losses in magnetic frame, temperature rise of transformers, advantages with a higher maximum flux density, reduction in core section for same output, decrease in mean length of turn of windings, therefore savings in copper material. Decrease in weight of transformer in turn, reduction in overall cost. Disadvantages. Increased magnetizing current since large ampere turns required. Higher no load losses. Saturation of magnetic material. Lower efficiency. Higher temperature rise. Types of sheet steel for transformer. Two types of sheet steel used for core and yoke. Hot rolled silicon steel. Value of Bm is equal to 1.2 to 1.4 Tesla for power transformers. Bm value 1.1 to 1.3 Tesla for distribution transformer. That is common for 1.2 Tesla hot rolled silicon steel. Cold rolled grain oriented silicon steel. Bm value is 1.5 to 1.7 Tesla for power transformer. Bm value is 1.4 to 1.5 Tesla for distribution transformer. That is cold rolled grain oriented silicon steel common 1.5 Tesla for two transformers.